Alright, number one, they want you to determine the end behavior. So the first thing you want to do is write this in standard form. So we're going to move these terms around a little bit. So we have the largest exponent here being the first term. There's a couple things that we can zoom in on or focus in on here, and that would be the fact that this is an even function and the fact that the leading coefficient is positive. Whenever you have a positive leading coefficient with an even function, it doesn't matter what degree it is, the ends are going to both be pointing up. So when we write our limit, the limit as x approaches positive or negative infinity is going to be positive infinity. Number two, first we want to write this in standard form, and it already is in standard form. The two things we can point out is that it's an odd function since it's cubed, and it's a positive lead coefficient. That means, if we were to take a look at the graph of it, it's going to rise from the left to the right. Now, whatever happens in between here, it doesn't really matter. I mean, it could go up, then down, then back up. It could just kind of ease its way up instead of going back down. It doesn't matter what happens in between. What matters is that from the left to the right, it goes up. So when we write this, the limit, we have to split it up because it's an odd function. As x approaches negative infinity, is going to be negative infinity, because as I go left, the graph goes down. And the limit as x approaches positive infinity is going to be positive infinity, because as I go right, the graph goes up. Number three, they want you to find different things. The end behavior, they want the turning points, and they want the intervals. Well, the end behavior, let's do that first. It's in standard form, it's an odd function, and the lead coefficient's negative. That means from the left to the right, it's going to go downhill. And again, like I mentioned, number two, it doesn't matter what happens in between. It could look like this, for all we know. It could look more like that. It doesn't make a difference. The idea is that it's going downhill from left to right. So the limit as x approaches negative infinity is going to be positive infinity, because as I go left, my graph goes up. And the limit as x approaches positive infinity is going to be negative infinity, because as I go right, it goes down. So that's the end behavior. For the turning points and the increasing decreasing intervals, I need to find out where the turning points are. So I'm going to get my graph out first, my graphing calculator. Let me move it over here. So let's clear out anything that we already have. So negative 4x cubed minus 5x squared. I'm going to graph that. And we see that our turning points are going to be here and here. So I'm going to zoom in on that area. And to the right. So here's a turning point here and here. So to find this one, it's a local minimum because it bottoms out. So second trace 3. We go over to the left of the point, to the right of the point, and then enter again. So this local min is going to be negative 0.83, comma negative 1.16. So let's write that down. So for the turning points, one of them is going to be negative 0.83 and negative 1.16. Let's find the other one. This one over here is going to be a local max. So second trace 4, go to the left of it, go to the right of it, and then enter again. Now I mentioned in class that e to the negative 6, e to the negative 11, this means that they're so close to 0 that we're just going to say 0 for both of these. So 0, 0, and you can see that this hits at the origin over here. So let's write that down. So those are our turning points. The increasing, decreasing intervals, what we want to do is we want to take a look at what this graph looks like. And let's just get like a little picture of it over here. Something like that. Just to get an understanding of where it's negative, where it's positive, and then where it's negative again. Again, the two turning points were here and here. It's positive from here to here, and it's negative from there to there, and there to there. So the increasing interval is going to be from the x value of this point, which was negative 0.83, to the x value of this point, which was 0. That's the only increasing interval. For the decreasing interval, it's going to be from negative infinity to the x coordinate of that point, so negative infinity to negative 0.83, and from the x coordinate of this point to positive infinity. So it's going to be 0 to infinity. And you're done. Number 4, we had another one of these. So let's do the end behavior first. So the end behavior, it's an odd function with the lead being positive. So that means from left to right it's going to go up. I mean, it could look like this. Doesn't matter what happens in the middle, just the ends is what we're concerned about. So the limit as x approaches negative infinity, you see it goes down, so it's negative infinity. And the limit as x approaches positive infinity, it's going to go up. So it's positive infinity. So this is the end behavior here. Next, we need to find out what the turning points are. So let's clear this one out and type in the new one, 3x to the third minus x minus 3. It looks like we'll have to change our window back to where it was. Let's see if it's in here now. Yeah. So what we're going to do is we're going to zoom in just over here. So let's make a box around this. And we'll see right over here is like a little local max. Over here is a local min. So second trace 4 would be the maximum, so we want to go to the left of that, then to the right of it, and then guess. So negative 0.3, comma negative 2.78. Let's write that. So these are our turning points. So it's going to be negative 0.33, comma negative 2.78, and there'll be another one. Let's find out where that one is. So second trace minimum, since it bottoms out, so just to the left of that and to the right of it. And this one is 0.33, comma, negative 3.22. So those are your turning points. And again, the graph looks like that. So just to keep that in the back of your mind, looks something like this. Right here are the, well, let me make this a little bit better than that. So your max and your min, it could have been better, but just to give you an idea that it's positive, then negative, then positive. So the increasing intervals, you're going to have two of them. From negative infinity to the x-coordinate of that point, which was negative 0.33, and from the x-coordinate of that point, which was 0.33, to positive infinity. The decreasing interval is going to be from the x of there to the x of there, so negative 0.33 to 0.33, and you're done. Alright, determine the degree of the polynomial. So first check to make sure that the x's go up by a constant amount. So, and it does, it all goes up by 1. So 4 minus 1 is 3. 1 minus 2 is negative 1. 2 minus 7 is negative 5. 7 minus 16 is negative 9. So the first difference doesn't pan out. So we got to do it again. 3 minus negative 1 is 4. Negative 1 minus negative 5 is 4. Negative 5 minus negative 9 is 4. So the second works out, so it's a second degree polynomial. Alright, so we want to find an equation for the volume of a box. So let's say this was your box here. And we got length times width times height. You want to keep that in the back of your mind. The length is 5 less than the width. So let's just label width W. That means the length is going to be 5 less than that, or W minus 5. The height is 3 less than this, so that's going to be W minus 3. To get the equation for the volume, you're going to have W times W minus 5 times W minus 3. So let's first multiply this in. So we're going to have W squared minus 5W times W minus 3. And then when you FOIL this out and collect your like terms, you're going to have W cubed minus 8W squared plus 15W. So that's going to be your equation. So we'll just say it's the function. Now they want you to graph it. Well, that's where a graphing calculator will help out. So let's clear this out. Let's reset the window. Alright, so let's type this in. So x cubed minus 8x squared plus 15x. Now let's look at the graph, just so we have an idea of what it looks like. Now let's do second graph, which is a table. This is going to be all points on the graph. So we have 0, 0, 1, 8, point here, 2, 6, and 3, 0. Let's do 2 of them at a time. 4, negative 4, and 5, 0. 6, 18, so we know this is going to be really high. And then let's just look at the graph one more time, just so we have an idea. So it's going to go up, hit this, go up here, hit that point, then go down, and then go right back up again. So let's try to draw that as smooth as we can. It could have been better over here, but close enough. So we've graphed the equation. Now, for which interval does the graph increase? We need to find our turning points, because whenever we're finding intervals, we have to get the turning points. So there's a turning point here and a turning point here. So let's figure that out exactly. So second trace max, it's right around here. So we're going to go left of that, right of it, and then enter. So 1.21 and 8.2. So we get 1.21 comma 8.2, and let's do the local min here. Second trace 3, anywhere to the left of it, to the right of it, 4.12 and negative 4.06. So 4.12 and negative 4.06. Alright, so let's just write down, these are all, this is where it's increasing, and this is where it's decreasing, and then increasing again. So we have two increasing intervals. So for part C, we're going to have two answers. So from negative infinity to the x-coordinate of this point, which is 1.21, and from the x-coordinate of this point to positive infinity, so 4.12 to infinity. It decreases from the x-coordinate of there to the x-coordinate of there, so 1.21 to 4.12. Alright, solve the system. So what we're going to do, since both of these equal y, we're going to set them equal to one another. So negative 2x plus 3 equals x squared minus 3x minus 7. Let's move all the terms over to the right-hand side. So if we add 2x, we're going to get minus x. If we subtract 3, we're going to get minus 10. This is not factorable at this point. So what we can use is the quadratic formula, or completing the square, it doesn't matter. So the opposite of b plus or minus the square root b squared minus 4ac all over 2a. So this is 1. The denominator is going to be 2. Negative 1 squared is 1. Negative 4 times 1 times negative 10 is 40. So we're going to have 41 inside. So 1 plus or minus root 41 all over 2 is your x values, or are your x values. Remember, you're solving a system of equations. Your answers are coordinates. You're not just solving for the solutions for x. So we have two answers for x. One of them is 1 plus root 41 over 2, and the other one is 1 minus root 41 over 2. So we need to find out what the y's are when x is this. So let's plug in x for x here. So negative 2 times x plus 3. This 2 and 2 cancel. So we're going to have to distribute the negative in here. So negative 1 minus root 41 plus 3. Negative 1 plus 3 is 2. So we're going to have 2 minus root 41. If I plug this in here, the only thing that's going to change is this sign here, which becomes that sign, which becomes that sign. So the only thing changing is this sign. So I can just write in 2 plus root 41, and those are my two coordinates. Those are the 2 points of intersection. Alright, what's the discriminant? Remember, the discriminant is b squared minus 4ac. It's in order, so b squared minus 4ac is going to be 9. Negative times a positive is positive. 4 times 2 is 8. 8 times 10 is 80. So my discriminant is 89. And what that tells me is that I'm going to have 2 unequal real roots. Number 9. So I have an I in the denominator. Can't have that. So what we have to do is rationalize it. We do that by multiplying the top and bottom by the conjugate of the bottom. So 3 times 2 plus 3i is going to be 3 times 2, and then 3 times 3i. Down here we have conjugates, so I'm just going to multiply the f and then the l in FOIL. Negative 3i times positive 3i is negative 9i squared, which is positive 9. So it's going to be 6 plus 9i all over 13. Can the graph of a polynomial function be a straight line? Explain your answer. The answer is yes. The reason why is because this is a polynomial function. It's got 2 terms. First degree. That's a straight line. So there's an example right there. The reason is, in general, because a polynomial can have 1 or more terms, and a straight line can be 1 term or 2 terms. You can have straight lines. You could have y equals mx plus b. That's 2 terms. Or you could just have y equals x. Or x equals a number. Like x equals 5. That's a straight line. Though it's not a function. Y equals 6. That's a function. That's a straight line. So that's the answer. And that's it.